Okay, so last video we saw how when we tried to measure momentum for the particle in the box, what we had to do is we had to recast the sine function in terms of two different exponential functions, e to the ikx, oscillating imaginary exponential functions, and the two of those functions corresponded to eigenfunctions of the momentum operator, which is basically the first derivative. And furthermore, the eigenvalues of those two functions corresponded to equal and opposite values of the momentum. So when we went to measure momentum, we would either get this leftward, rightward going, let's say, momentum, or leftward going momentum 50% of the time each. So let's generalize that a little more now. Consider basically any operator. If you got to measure some quantity, okay? I don't know what it is. Favorite ice cream, something. There's got to be a corresponding operator that relates to that measurement. And let's call it O hat, right? We're always going to have a hat. And you're going to get an answer, and I'm going to call that little o sub n, with a little tail on that. Looks kind of like a sigma, but that's an O, little o sub n. So remember always, when you make a measurement on a quantum system, that corresponds to munching on the wave function with an operator. It's some kind of mathematical manipulation, whatever that happens to be. You do it, and you will get an answer. And it's going to correspond to some value that we're going to call O sub n. Now, O sub n, the answer you get, is going to be one of the eigenvalues of the operator O, big O with a hat. And if at the beginning the wave function of the system actually is an eigenvalue, so psi is not an eigenfunction of O hat. So if it is an eigenfunction of O hat, then you're just going to get one number, one little o, and that's going to be the eigenvalue of psi. But if psi is not an eigenfunction of the favorite ice cream operator O hat, then you have to do something. We've got to take matters into our own hands. We've got to take some measures. And so now this bit is what those measures are in general, okay? Now, what are the measures? They're fairly straightforward, but it's a little detailed, so we're taking this slow. So we're going to take that wave function psi of x, and we're going to recast it, just like we took sine and turned it into two flavors, the sum of two flavors of Slinky. We're going to take psi of x and express it as what we call a linear combination, a sum of other functions. Phi1, Phi2, Phi3 are the functions. C1, C2, and C3 are coefficients of those functions. So Phi1, Phi2, Phi3 are functions of x. They change as x changes. C1, C2, C3 are constant coefficients. It turns out we can always do that, and we're going to, generally, we're going to sum over some index variable, the coefficients times the function phi. It could be 540 of them. It gets kind of boring to write it out, so we use the summation notation. So Phi1, Phi2, and Phi3 must be properly normalized eigenfunctions of the operator, big O hat, your favorite ice cream, whatever happened, whatever it is we're trying to measure. They have to be properly normalized eigenfunctions over the interval if it's confined, or whatever the normalization is. Integrate over all space. Address the Born hypothesis that if you ask the object, where are you, It's going to answer somewhere with unit probability, so it has to be properly normalized. That's the first bit. So they're what we call a proper basis set. Now, so remember, for the normalization, we integrate from -1 to infinity, phi sub I star, the complex conjugate, times phi sub I, and it's got to be 1. Okay. Now we got these coefficients underlined in green. So those we call the coefficients of each phi. And it turns out, as we saw with the two coefficients that were each 1 over a square root of 2, it's always true that the sum of Ci star times Ci is going to be 1. And that's a very, very good and very important thing. And again, that's the check. So whenever you have a situation like this, you should square all those coefficients, add them up, and make sure that it comes out to 1. And then psi of x is the original wave function, which also has to be properly normalized. So it turns out we can always do that. We can take a function and we can express it as a linear combination of other functions. And ultimately we're going to wind up understanding and expressing these things as what we call orthonormal basis sets. So phi is an orthonormal basis set, and we can always do this. We're going to do some exercises. The ortho part means orthogonal, and we're going to get to that on Wednesday in the next lecture, but we already know what normalization means. So again, we've taken our wave function, psi of x, and we've cast it in this new form. It's equal to C1 phi 1 plus C2 phi 2 plus C3 phi 3, and the sum of C squared for all the C's has got to be 1. So each C, I'm going to use J as the indexing variable because we got these I's in the as an imaginary number, so let's call it Cj, is always going to be equal to some amplitude Aj, and then there's going to be some imaginary part to that. So it's going to be e to the I times an angle. And remember the 1 over minus i's and 1 over i's and things last time. That was a manifestation of this. So there's going to be some imaginary complex number of amplitude 1. It could be 1, could be I, could be minus I, could be minus 1, or could be any appropriate, square root of 2 plus square root of 2I. Doesn't matter. We can break it apart this way, and then those AJs are really easy to understand. So that there's the imaginary bit you can basically not worry about the complex bit in that regard. And the reason is that when we go to do the find the coefficient, we're going to take the coefficient times its complex conjugate, and that corresponds to taking e to the I times whatever angle that is, e to the I theta j, times e to the minus I theta j, because that's what a complex conjugate looks like, and that's just 1. So that just turns itself into 1 when we do our magnitude squared. And so then A, which is positive definite, is the amplitude we care about, and we just square it. So it's just A squared. So if you go to measure some observable, this value O, with operator capital O hat, favorite ice cream type, whatever it happens to be, then you're going to obtain the value O sub j with the probability AJ squared. That's it. And that's why the sum of AJ squareds have to be 1, because you're going to measure something for sure. And you're not going to measure more than something. It really has to be exactly 1, just like normalization. It's another example of normalization. And again, O hat, the operator operating on these phi functions, which are eigenfunctions of O hat, will give you O sub j, the observable for the operator O hat times the basis function. It's an eigenvalue, and phi j is an eigenfunction, and it's a standard eigenvalue-eigenfunction relationship. So again, we have the operator O hat, which is some sort of Typically, often it's differentiation. There's other things that we'll see later. Um, Phi is the are the eigenfunctions, and there's a bunch of them, often infinite, almost always an infinite number. We're going to call that a basis set over time. And then in this eigenvalue expression, O hat operates on phi sub j, the eigenfunction, and out poops the eigenvalue, the observable O sub j, times again the eigenfunction phi sub j. And the probability of getting that answer O sub j is equal to that coefficient, that amplitude A sub j squared. So I'm being repetitive here because I think this is a concept that takes a little while to wrap your mind around, and I want to repeat what we're doing with the basic simple solution that we've been working with, which is the particle in the box. So once again, let's assume that we're starting with our particle in the box wave function, root 2 over L, sine of n pi over L times x, and then we cast that into the basis set of momentum operators. So we have the square root of a half times 1 over I times the square root of 1 over L e to the in pi over Lx, and then plus the square root of a half times minus 1 over I times the square root of 1 over L e to the minus n pi over L times x. So I've done what we were talking about on the previous slide. We've taken the amplitudes and then a complex function with amplitude 1, which is the 1 over I and the minus 1 over I, and pulled them apart. So those things there, underlined in red, are the basis sets. The square root of 1 over L e to the in pi over Lx, and square root of 1 over L e to the minus in pi over Lx. That's phi plus and phi minus, and that square root 1 over L is incredibly important. They are properly normalized functions. Again and again and again, we have to keep that in mind. And then these amplitudes are the root 1/2, and that would be the amplitude A plus and the amplitude A minus. Notice when I said A sub j, phi sub j, j doesn't have to be 1, 2, 3, 4, 5. It doesn't have to be an ordinal set. It just has to be a distinguishing value, right? So in this case, it could be potato and tomato, and that would be kind of weird, but it would work. So we're using plus and minus in this case because the answer has this unique attribute that that we get the positive and negative values. So A plus squared is a half, and A minus squared is a half. So this is our 50-50. The probability of getting one value of the momentum or the other is just 50-50. So psi, which is basically sine, is an eigenfunction of the Hamiltonian for the particle in the box. But if we go and we measure momentum, we've established again that sine is not an eigenfunction of the momentum operator p hat, which is minus I h bar d by dx. So it doesn't work. And then we have to do this business of recasting the wave function as we did just above. And you can always do that. So we find another way to express it where we do have eigenfunctions of momentum, and then we merrily measure momentum, p. And we're going to get p plus 50% of the time and p minus 50% of the time, because that's a plus squared and a minus squared. And we can concisely write this as p plus or minus is plus or minus h bar times pi divided by L, all times the quantum number n. So finally, we can think about this in terms of just pure physical meaning, right? This always has to come back to something that has some physical meaning. For the situation of the particle in the box. I mean, I've been jokingly calling things favorite ice cream operators and whatnot, but momentum is momentum, a nice, solid physical property. But remember, momentum has direction to it. So if we got our box again, here's the x-axis, and the potential goes to infinity at 0 and L. So we're confining ourselves to being between 0 and L. We just have, well, all it's saying is that if we go and we ask the particle, what's your momentum? If it's got energy, it's got to have momentum. And P plus just means I'm moving to the right. with some speed, some momentum, which is just the velocity times the mass. So some of the times it says, hey, I'm going to the right. And some of the other times, P minus says, no, I'm going to the left. Well, that has to be right, right? This makes a ton of sense. If you measure momentum and you've got this particle stuck in a box, what is it doing? It's bouncing off the walls. So half the time, it's going to be going to the right. It's going to be going to the left is the way I wrote it. So half the time it's going to be going to the left and you're going to get P minus. And half the time it's going to be going to the right. And it's literally bouncing off the walls. The poor thing. Think of it as a little super ball. Bang, 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 going each way. This makes a ton of sense. So you go to try to measure the momentum at some moment in time. Maybe it's going to the left. Maybe it's going to go to the right. And the probability of getting one or the other is just 50-50. So it's completely sensible. Often, the things you get out of, in the end, make sense. Sometimes when the scale is so minute, answers are surprising. But in general, what you finally get out of this when you think it through, it's perfectly sensible. And this is an example of that.